Our last speaker for the session will be Andrew Branch. Andrew is a member of the technical staff in the Artificial Intelligence Group of the Jet Propulsion Laboratory at California Institute of Technology. Let's see Andrew's video, please.
Everyone, I'm Andrew Branch from the Jet Propulsion Laboratory's Artificial Intelligence Group, and today I'll be talking about autonomous operations for an ocean world submersible. Ocean worlds are bodies in our solar systems with liquid water oceans, the most well-known of these besides Earth being Europa and Enceladus. In order to explore any significant portion of these oceans, a new mission concept will need to be developed, specifically an ocean world submersible. On the right, you can see a diagram of what such a mission might look like. A surface antenna would be deployed on top of the icy shell. Cryobot would bore through that icy shell and deploy a base station on the underside of the ice and deploy a submersible into the ocean itself. This submersible would have an acoustic communication link with the base station, which could then talk through the surface antenna and back to Earth. There would be limited communication due to orbital occlusions and limits in acoustic communication range, as the vehicle may be distant from the base station, potentially hundreds of kilometers. For such a mission, full autonomy would be needed for weeks at a time. Here we have a list of potential autonomy requirements for such a mission. First, to maximize the science return, we want to enable the discovery and tracking of scientific features of interest and the use of expendable science experiments. Second, the vehicle would need to be able to autonomously navigate and transition between different navigation paradigms. Depending on how the mission's designed, the vehicle may also need to do autonomous docking. We would need to do activity planning, so deciding when to do science, when to return for communication, when to actually do that communication, those types of things. And finally, we need to be able to autonomously recover from faults in case something doesn't go quite as according to plan. We have a number of prior and ongoing works developing some of these autonomy requirements. The first category being autonomous science, so the ability to autonomously locate and track scientific features of interest. The first effort here is led by Chris German out of Woods Hole, where we are looking to autonomously locate sources of hydrothermal venting by taking observations of the hydrothermal plume. In this project, we took the traditional manual-based search method that has been used many times in the field and developed a fully autonomous version of that. And in a second project led by Andrew Thompson out of Caltech, we developed methods for oceanfront tracking using in situ data and the targeting of mesoscale ocean features using predictive ocean models. This work was deployed to Monterey Bay in 2016 and 2017 and was done in collaboration with Woods Hole, Mbari, and Caltech. We also have work developing the autonomy required for navigation. The objective here is to develop navigation methods and autonomous behaviors to transition between different navigation paradigms while still being able to perform autonomous science. On an ocean world mission, you might expect to have multiple types of navigation. So if you're very close to your beacon, you may get range and bearing from a USBL. A little bit further away, maybe you get range only. Even further out from that, you may not have contact with your acoustic beacon at all. So how do you transition between these different regions while still achieving your actual end goal of taking scientific data and returning that scientific data back to Earth? In this project, we have a deployment in October of this year with the Monterey Bay Aquarium Research Institute to test some of these autonomous behaviors. Along with the ocean world's application, there are a number of terrestrial use cases for this type of autonomy. It would enable long-duration under-ice exploration as it has similar communication constraints, as well as enable large-scale ocean observing systems where you might not be able to micromanage all assets. It would also enable the targeting of transient oceanographic features when it's not possible to have humans in the loop. The next steps are to continue to refine these individual autonomous behaviors, as well as integrate them and perform in-water testing of end-to-end autonomy that would be similar to what you would actually put on a submersible on an ocean world, and of course look for applications for this autonomy to improve terrestrial science operations. Thanks.
Thank you so much, Andrew. That's a very exciting talk, moving some of our ideas from our oceans to those to other oceans on different worlds.